Hey, good morning, everyone. Thank you so much for joining us at this live stream. We already have quite a crowd, so let's just dive right in. First, I want to give a big shout out to all of you for being here. I'm Anya. I'm the business development manager at Kmine. And before we kick things off, I just want to remind you all to hop over to our LinkedIn page. We share all of the latest updates, announcements about our future streams there. So make sure you hit that follow button. But today we're going to delve into a highly significant topic for geologists and mining engineers. Our focus will be on the top 5 tips for mineral resource estimation. And today with us is Kmine geologist Tatiana.
Hello, Anya.
Hi.
Hi.
Hi. So Tatiana will answer your questions in the end of the stream. So if you're interested in understanding common mistakes to avoid and getting insights into effective techniques for the mineral resource estimation process, this webinar is must watch for you. So let me give you a quick rundown of what our mining software company brings to the table, apart from the features we'll dive into later. We've been on the market for nearly 30 years, offering a standalone application that can be tailored to fit your company specific needs. Our solution is all about flexibility, and it's because of its modular design. It's a perfect fit for business of any size. Plus, we've got your back with reasonable pricing options. And our application is powered by our very own patent graphic core, which enables fast information processing. Generally, our goal is to cater to a wide range of operational needs, including 3D modeling, resource estimation, planning, and we currently have developed 12 models specifically designed for companies involved in exploration, development, and production stages. These models are highly configurable, adaptable, and can be enhanced to suit each deposit, whether it's open pit or underground mining. The beauty of our system lies in the fact that each of these 12 models can function as a standalone application or seamlessly integrate with one another. This eliminates the hassle of creating SharePoints, dealing with compatibility issues, wasting time on import and export processes, or tedious data adjustments. It provides different departments within a company with a unified platform to exchange information effortlessly. Moreover, we've got you covered with custom solutions and comprehensive planning services to automate production stages and streamline your entire workflow. At Kmine, we truly understand the unique aspects of each mining project. That's why we go the extra mile by offering the services to mining companies throughout the exploration, development, and production stages. Our team includes mining engineers, geologists like Tatiana, planners, surveyors, and a bunch of other industry professionals. With their expertise, we can provide a wide range of services from resource modeling and mining engineering to auditing. So our engineers not only implementing our solutions, but they also set up our entire company's infrastructure, support you at any stage of your project. So whether it's creating detailed 3D models, planning schedules, or estimating resources and reserves, we're there to assist you every step of the way. So if you're curious and want to dig deeper into the specifics, don't hesitate to reach out to us. We'll be happy to chat. All right, so let's just dive into the topic of the webinar. So when it comes to the world of geology and mining engineering, professionals like yourself often come across a whole bunch of questions and challenges. Today, we aim to address some of these queries. And first and foremost, the quick question of block size when creating a block model. What factors should one rely on when making this crucial decision? And what prevents the utilization of a minimum sub-block size during the interpolation of content? Next up, we'll shed the light on the most prevalent mistakes in the allocation of mineral resource categories. Understanding these pitfalls is key to avoiding them and ensuring accurate categorization. After that, we delve into the complex procedure of delineating ore bodies within polymetal deposits. These deposits consist of multiple valuable components, each with unique technological indicators during the enrichment process and different costs also for the final marketable product. So it's essential to effectively navigate this complexity. And moreover, we'll examine various approaches for dealing with individual samples that exhibit anomalous content, and we will uncover the appropriate methods to apply in the specific cases. And lastly, we will highlight the importance of accurately determining the volumetric weight of ores. We will explore different interpolation methods to ensure the precise estimation. All right, so let's talk first about a block size. The parent block size stands as a paramount parameter that influences accuracy of grade estimates within a resource model. When determining the block size for a block model, various factors come into play, including things like mineralization controls, geometry, mining method, spatial distribution of drill holes and samples, and the anticipated grade control method. If you choose a block size that is too small, it leads to excessive smoothing of grade estimates, ultimately yielding an inaccurate grade to tonnage ratio. On the other hand, if you select the block size that is too large, it's also useless in pit optimization and mine planning. For example, in K-Mine's mine planning model, which is called scheduling model, the block sizes are set to match the time intervals indicated in the mine plan. So to illustrate the impact of the block size selection on tonnage and grade calculations, let's consider the graphite deposit scenario. So on the slide, you see on the left, we have a block model with a block size of 120 meters with an average grade in the ore of 3.14% and maximum grade in the block of approximately 9%. On the right, we observe a block model with a block size of 30 meters, exhibiting an average grade in the ore of 4.13% and maximum grade in the block of about 14%. So when it comes to assessing mineral resources, the choice of block size plays a big role. It has a significant impact on how we calculate the tonnage. For example, with a cutoff grade limit of 3%, the difference in tonnage calculation is 20%. So you can see how important it is to carefully consider the block size when determining mineral resources. Experts commonly recommend determining the block size by taking into account factors like drill hole spacing, technical parameters, and according to several researchers, a practical approach is to set the block size at approximately 1/3 or 1/2 of the distance between drill holes. This suggestion is based on the knowledge that smaller block sizes can introduce artificial smoothing into the model. When neighboring small blocks are evaluated using the same samples, they tend to yield similar scores. On the other hand, if the block size is too large compared to the drill hole spacing, it fails into fully utilize the density of exploration network that has been achieved. So when it comes to evaluating grades within the blocks, it's a good idea to keep in mind a general rule of thumb. Consider a range of at least 1/4 of the average density of the exploration network. This helps ensure that we account for variations and have more comprehensive assessment of the grades within those blocks. Another crucial factor influencing the decision regarding block size is the estimation of recoverable resources when it encompasses the concept of selective mining unit or SMU. In mining applications, when conducting estimates, we often aim to map the spatial distribution of mineral attributes based on the block support rather than sample support. So selective mining unit refers to the smallest volume of material used for determining ore or waste classification, and it is derived from geostatistical estimation. It represents the minimum unit that can be selectively mined. But here, something to keep in mind though, the smallest mining unit is usually way smaller than the sampling grid dimensions where we can collect information. This is particularly true during the exploration and feasibility stages. So when we try to estimate values to these tiny blocks directly, we often end up with a low precision. When we directly interpolate small blocks, it also has a big consequence. It messes up the grade tonnage curves. In other words, if we base our prediction of attribute content above a certain cutoff on these estimates, we can end up way off from reality. So to solve this issue, there are two options on the table. First, we can set the contact boundaries separately from the accuracy estimate. So, for example, here how it works, we start by determining the size of the elementary blocks based on the sampling network. Then we fill the subblocks with estimates from the parent blocks. The second option is to bring percentage calculations into the picture when we are assessing volume. So it comes down to this: should we use parent blocks to assign scores to subblocks, or we should go with the block models that allow for percentage calculations? So it's important to make the right decision, since we should be sure that we get accurate and reliable estimation of recoverable resources and mining applications. When it comes to K-mine, both of these approaches are actually available. In case of a cubic block model, we use sub-blocking system. Users can easily select a block model with parent blocks and generate a new model based on this. But all attributes would be automatically loaded, requiring only the specification of a new block size that is multiple of the original size. When reducing the block size, the score of the parent block is assigned to the sub-blocks. So conversely, if there is a need to increase the block size, attribute values can be recalculated using one of three formulas: weighted average by volume, weighted average by tonnage, or maximum value assignment. This is where we assign value to the original subblock that occupies the largest volume within the new larger block. For a cubic seam block model, K-mine utilizes an algorithm to calculate the percentage of seam volumes that fall within each block. Depending on the ratio of seam volumes within a block, other parameters such as content, specific gravity, also weighted. In this situation, we start off by figuring out the percentage of material volume in each block, and once it's done, we estimate the grades for each geologic unit. And the grand finale comes when we calculate the final average block grade as a weighted average for all geological units found within that block. This approach not only reduces the number of stored blocks, but also gives us more variables to work within each block. Some softwares also offers mathematical analysis methods to determine the optimal block size. One of such methods is Kriging neighborhood analysis, or KNA. KNA generates statistics that measures conditional bias, which reflects the extent of oversmoothing in blocks in estimates compared to the theoretical true values of grades at that block. So the goal of KNA is to identify the parameters like block size, numbers of sample, search radius, discretization that minimize conditional bias in the estimation while avoiding excessive negative weights. And there are two key statistics that are used for optimization. First one is Kriging efficiency. It tells us how well the Kriging estimate accurately reflects the local block grade. Kriging efficiency measures the effectiveness of the Kriging estimate to reproduce the local grade accurately, local block grade accurately. So it's computed by comparing the Kriging variance of the block with the theoretical variance of the block. Lower Kriging efficiency indicates a higher degree of oversmoothing, while higher Kriging efficiency indicates a lower degree of oversmoothing. And the second statistics used for optimization is slope of regression, or conditional bias slope. This statistic summarizes the degree of oversmoothing for high and low grades. It represents the regression slope of the estimated block grades against the corresponding true yet unknown grades. Ideally, the optimal result is a slope of 1 and Kriging efficiency of 100. However, in reality, in practice, common values typically fall within the range of 80, 90%, something like that. So by leveraging methods like KNA, software users can analyze and justify the optimal block size by considering the statistical measures of conditional bias and ensuring a balance between oversmoothing and accuracy in grade estimation. Another important aspect to take into account is the differentiation between spotted dog and continuity, especially when we're discussing resource classification. So when it comes to evaluating mineral resources, one of the key elements is gaining a solid understanding of ore controlling structure and precisely defining mineralization zone and ore bodies. It plays a vital role actually in ensuring accurate estimation and effective resource management. The classification of resources is reliability of these processes. So to illustrate the point, there's this compelling example just to showcase 7 different delineations of ore bodies based on the same set of ore intersections. This somewhat lighthearted image highlight the significant influence that the expertise of specialists has on interpreting exploration results. In addition to collecting numeral data through sampling intervals, it's crucial to consider and utilize knowledge about the physical characteristics of ore bodies in different types of deposits. This includes understanding of influence of tectonics, the presence of secondary processes, and other relevant factors that shape their morphology. Despite the numerous benefits of computer technology in the field of mineral resource modeling and block estimation, there is a certain drawback when it comes to the widespread use of software products. Users often rely solely on the mathematical calculations embedded on the software, neglecting the analysis of algorithms and actual utilization of all available geological information. So this approach can lead to inadequately classified mineral resource estimates, giving rise to what is commonly known as the spotted dog effect. Here's a lowdown. During the resource estimation, there is this interesting thing that happens. We usually use just statistical analysis to figure out the radii of the anisotropy ellipsoid, and then we bring in the big guns, one of the Kriging methods, to estimate blocks. Now, in regions when we have lots of samples or close to each other drill holes, our program works its magic and it determines the high level of reliability for the measured category. But when we're dealing with those remote areas where samples are limited, and we switch gears and rely on the indicated category. As a result, isolated spots or ring structures of the measured category appear with the spaces between them filled by the indicated category. This approach sometimes overlooks crucial factors such as lithology or fault system that controls mineralization. The specialists rely primarily on value indicating the reliability of the estimated content in blocks, such as the number of samples and drill hole use, the number of iterations, Kriging variance, regression slope, relative distance from data points, and proximity to nearest drill hole, average distance to mouth, and more. While these values are helpful in assessing the confidence of content rating, they should be considered only as initial step in the mineral resource classification process. It's vital to take broader aspects into account, including confidence in geological interpretation, data quantity, distribution, and quality. Practical solutions exist to address these challenges, such as, for example, the development of resource categorization frameworks that can be modified based on the Kriging variance. However, these frameworks are applicable mainly to rare cases that involve massive single ore bodies. When dealing with a large number of cases, we can consider the use of so-called categorization smoothers through the computer functions. So this tool helps us achieve smoother boundaries for our resource categories. The competent person should also consider additional criteria when making a decision, such as the reliability of drilling data, structural interpretation, asset database, the feasibility of economic extraction, metallurgical test work, geotechnical data, permitting considerations, social acceptability, legal and land tenure factors, and so much more. But regardless of the criteria or methods that are employed, it's crucial to document them in sufficient detail so others can reproduce the results. And here's the deal. When it comes to mineral resource models used in estimating mineral reserves, we're all about teamwork. We encourage collaboration between practitioners and mining engineers to select estimation parameters that meet everyone's needs. Now, here's a tip. A practitioner should aim to synchronize mineral resource classification parameters with the practical constraints of potential mining methods. Try to match up boundaries with mining levels, stop ages, zone boundaries whenever it's doable. It's all about finding this perfect harmony between your resource classification and the real world mining operations. So, to ensure compliance with the reporting standards such as JOR code, SAMRA code, and I-43, CIM, and SKI 1300, it's essential to consider the requirements for continuity in your report. Continuity refers to the correlation between drill holes rather than contouring around the individual drill holes. Well, if you examine these codes, you'll be surprised by the frequency with which the requirement for geological and grade continuity is emphasized throughout the text. Yet, despite this emphasis, there are still errors in the classification of mineral resources based on continuity. So allow me to share some of the relevant quotes from NI43 and SIM best practice guidelines that highlight the significance of continuity in the classification of mineralization geological features. You can see on the slide that the requirements for continuity of mineralization or geological and grade continuity can be found in various sections of this document. And by understanding and adhering to a principle of continuity as outlined in these codes, you can ensure that your report meets the necessary standards and provide a robust assessment of the mineral resources in question. Let's take a closer look actually at the significant definitions provided by JOR code. In the JOR code, the definition of mineral resources, both in general and by category, highlight the importance of the continuity requirement. For instance, the definition of a measured mineral resource in JOR code states that geological and grade continuity between points of observation where data and samples are collected must be confirmed through outcrops, trenches, pit workings, and drill holes. Similarly, the definition of indicated mineral resource emphasizes that there is a significant evidence to assume geological and grade continuity between points of observation where data and samples have been gathered. This definition underscores the significance of continuity in assessing and classifying mineral resources according to the JOR code. So here's a key to success. Practitioners can deliver precise and dependable evaluations of mineral deposits by making sure that geological and grade continuity is convincingly demonstrated throughout the range of data collection methods. So we can revisit the important aspects of the conversion of mineral resources to ore reserves, as well as the approaches to mine design and reserve estimation for underground mine. It's crucial to understand the distinction between indicated and inferred resources, since only measured and indicated resources can be converted to ore reserves. When deciding between the two, the competent person should consider the requirement for geological and grade continuity along with the specific guidelines mentioned in the definitions. Indicated mineral resources should exhibit sufficient confidence to allow the application of modifying factors supporting mine planning and economic evaluation. On the other hand, inferred mineral resources lack the necessary confidence for detailed planning and should be approached with caution in technical and economical studies. The presence of inferred resources poses difficulties for mining engineers in stope and pit design, since they can't be converted into ore reserves. So there are two main approaches that are employed in mine design and reserve estimation. So let's break it down. In the initial stages, like scoping studies, we often apply inflated coefficient for dilution and extraction factors. This is because we have limited information available at this point. To compensate for the lack of data, we often resort to using analogy method when we draw insights from similar deposits and production methods. It's all about making sure the best possible estimate with the resources we have on hand. As we move to later stages, specifically from pre-feasibility to a final feasibility study, we dive into the details. This is when mine designs are meticulously crafted for each individual stope. We take into account things like dilution, recovery factors, and other various parameters. It's a comprehensive process that considers crucial aspects such as backfill methods, geological structures, equipment capabilities, and corporate requirements. We also conduct thorough economic evaluations. We crunch numbers and analyze all of the factors at play. Stops that meet the company economic criteria, along with the other considerations such as metallurgical, marketing, legal, environmental, social, government factors, they have potential to be classified as ore reserves. It's the point where we determine the real value and potential of those precious underground resources. And when engineers start using block model for resource estimation, they encounter a tricky situation when it comes to determining the reserve category for stopes that contain a combination of mineral resources categories, unclassified materials, and waste. So there are two available solutions. First solution is to calculate weighted average of resource classification and then assign the corresponding reserve category. However, there is a drawback to this approach, as it may lead to the exclusion of indicated resource blocks from being converted into reserves, which is not an ideal outcome. For example, let's break it down with an example. Imagine a stope comprising 60% inferred resources with 40% indicated resources. In this case, the stope classification would fall short and it wouldn't be included in the reserve category. Fortunately, this results in a significant number of resource blocks not being converted into reserves. On the flip side, we encounter a stope where over 50% of discovered resources are measured, with the remainder being indicated and inferred. So it could potentially be classified as proved reserves. However, this approach artificially inflates the level of discovered and inferred resources, which also deemed unacceptable. Even if the stope's categorization is downgraded to probable reserves, the conversion of inferred resources into ore reserves will still violate the JORC code. It's a kind of like delicate balance. The finding the right solution is crucial to maintain compliance with the regulations and, of course, accurately reflect the true nature of the resources. So the second approach is to determine the tones and content of the resource categories in the stope and convert the individual resources to the appropriate reserve categories. This approach ensures accurate conversion, but there's another challenge, right? How to report inferred resources and unclassified material present in the mine, which may be treated as internal dilution or waste. So in conclusion, the competent person can rely on model block estimation algorithm, but also not solely base resource classification on them. Additional analysis and adjustments guided by the experience, knowledge of the deposit types, of course, are essential for accurate classification. So the same thing goes to extreme values. Determining what values are considered outliers is a subjective process. The competent person typically decides whether to exclude outliers from the sample or replace them with a different value. The term itself, outliers, refers to extremely high values, as many grade distribution exhibit positive skewness. A small number of very low or very high values can significantly impact summary statistics such as the mean, variance, correlation coefficient, and measures of spatial continuity. When it comes to dealing with data, it's important to handle things properly. So first thing first, we need to remove any erroneous values from the data set. However, when it comes to valid extreme values, we have a couple options. We can classify them as a separate statistic population and give them a special treatment during the processing. Or alternatively, we can employ robust statistics that are less affected by extreme values. So these options can be applied at different stages of mineral resource estimation, depending on the specific circumstances. So now here's the golden rule. We should avoid modifying the data unless we know for sure that there are errors present. However, it's worth noting that even valid extreme values may have limited influence on the spatial predictive models. So it's all about fighting again this balance between ensuring data accuracy and minimizing the impact on our predictive models. Assuming all potential database and analytical errors have been checked for and corrected, outliers are defined in terms of geological and statistical populations. Extreme grades have a significant impact on the calculation of average metal grade in ore. Therefore, when defining core sample content limits, it's important to work with the source database before compositing. Outliers need to be identified and decisions made regardless of their treatment during the resource evaluation. The influence of outliers on the resource estimation process can be assessed through statistical analysis. Notably, extreme grade values like those caused by hurricanes can have a significant impact on the final resource estimates. The degree of skewness in the grade distribution determines how outliers might affect source estimation. A common approach to examining outlier values is by using log normal cumulative frequency plot. So to identify outliers, several methods can be employed, including both visualization technique and statistical measures like z-scores or interquartile range or IQR, sorry. So if we talk about visualization method, there are two effective visualization techniques for outlier identification. One of them is a box plot. This graphical representation of numerical data uses quartiles and whiskers to depict groups. Outliers appear as individual points outside the expected range. The other technique is scatter plot. By displaying values for two variables on the Cartesian plane, scatter plots highlight outliers as points that deviate significantly from the main cluster data. So moving on to the statistical measures, let's talk about the z-score method. The z-score measures the number of standard deviation by which an observation deviates from the mean of the dataset. It rescales and centers the data, allowing the identification of data points that significantly deviate from the mean. Typically, to identify outliers, it typically used a threshold of plus minus 3. The other statistical measure is IQR method or interquartile range. It's a measure of statistical dispersion that represents the difference between the 25th and 75th percentiles, which are lower and upper quartiles. Similar to this core method, IQR method identifies the data distribution and applies threshold to detect outliers. So here's how you use the interquartile range. So first find first quartile, which is Q1. Then find the third quartile, which is Q3, and calculate IQR. So it's Q3 minus Q1. So to establish the range of normal data, you can define the lower limit by subtracting 1.5 times the interquartile range from the first quartile, and the upper limit by adding 1.5 times the IQR to the third quartile. This allows you to identify values that fall outside of the normal range. And any data point outside of this range is considered outlier. It should be removed for further analysis. So when we use a box plot, the IQR method comes in handy to spot any outliers in the data. You can identify the maximum point, which represents the end of high whisker, by calculating Q3 plus 1.5 times the IQR. Similarly, the minimum point, indicating the start of the low whisker, that can be determined by subtracting 1.5 times the IQR from Q1. So you can see the formula on the slide, actually. And let's talk about the 68-95-99 rule, also known as empirical rule. provides a way to understand how the data spreads within the normal distribution. So here how it goes. Around 68% of the population falls within one standard deviation of the mean. It's like saying the majority of the data stays relatively close to the average. When we extend the range to two standard deviation, approximately 95% of the population falls within that range. So what it means is that most of the data points still remain within a reasonable distance from the mean. Now let's widen the range even more to three standard deviation. In this case, about 99.7% of the population falls within the broader range. So it means almost all of the data points fall within the considerable distance from the mean. Quantiles, on the other hand, are pretty useful for comparing different distributions. They come in handy when you want to compare the distribution of the original data to simulated values, or when you want to analyze different types of samples, or even compare assay results obtained from different labs. During the resource estimation, it's crucial to model in situ density of the ore deposit. The estimated tonnage of the deposit relies heavily on the tonnage factor or density applied to the model volumes. So today we won't dive into the details of density measurement procedures. Instead, let's shift our attention to two important aspects: the number of density measurements needed and the influence of their spatial distribution on mineral resource and resource estimate. Determining the appropriate number of density measurements is the key. It ensures that we have sufficient data to accurately represent the density variation within the deposit. The spatial distribution of these measurements also plays a significant role. Ideally, we want them to be well distributed across the deposit, capturing the variability in density throughout different areas. So by carefully considering these factors, we can improve the reliability precision of our mineral resource and reserve estimates, leading to more accurate estimation and assessment of the deposit's tonnage and overall value. So let's talk about another approach to density estimation. In a study conducted by Arsenault, they delved into 50 technical reports that were filed on the System for Electronic Document Analysis and Retrieval, which is SEDAR. The aim was to shed light on the methods used in these reports and highlight some findings. So they are summarized on the slide. The study findings paint a picture regarding the handling of density data and resource reports. It revealed that despite collecting sample density data, the analysis and discussion of this crucial information were sorely lacking. The study examined a range of reports and made some discoveries. So here's what they discovered. Out of the reports reviewed, a mere 20% actually utilized a density-specific dataset. That means that the data was independently used to estimate density for each block in the block model, which is a crucial step in ensuring accuracy. Surprisingly, a significant 18% of the reports didn't discuss density at all, completely overlooking its importance. Even more alarming is that the fact that around 58% of the documents simply reported a single average density value without even considering the distribution of the data. So the statistics highlight the lack of attention given to density in the reviewed reports. In the past, the term specific gravity was commonly used to refer to the dry bulk density of rocks, but this term was now considered inaccurate and not recommended to use. Instead, the more appropriate term is dry bulk density, and it represents the dry mass of a rock excluding any natural moisture per unit of actual in situ rock volume while accounting for porosity. It's more precise and meaningful way to describe rock densities. Sample density is often correlated with sample grade due to the higher specific gravity of most metals compared to the host rock. When the concentration of metal is significantly high, it influences the density of the rock. Deposits such as, let's say, uranium, massive sulfides, iron, and some high-grade ore deposits typically exhibit a clear correlation between grade and density. The type and intensity of alteration can also impact in situ density values. Highly altered rock tends to be friable and powdery, resulting in lighter weight compared to unaltered rock. It's a common practice to define density domains based on the combination of lithology, alteration, mineralogy, and average rock grades. In mineral deposits with a low metal content and simple mineralogy, calculating the average of all bulk density measurements may be sufficient with adequate data and meaningful average. However, each geological domain should be examined separately, and distinct bulk density values should be calculated for each. For deposit with more complex mineralogy and the relationship between density and grade, simply averaging bulk density within each geological domain can lead to errors in local estimates and resource tonnage. A better approach is to apply similar interpolation parameters used for grade estimates. In deposits with high grade and density variability, weighting grades by density and estimating grade times bulk density can result in a more accurate resource estimate. The crucial question is how many density measurements are required to ensure accurate estimation of ore body and host rock tonnage. Typically, the number of dry bulk density samples ranges from less than 200 to several thousand, depending on size and type of the deposit. The proportion of dry bulk density samples to the samples collected for estimating metal grades varies from 5% to 96%. So let's look at JORC Table 1, specifically Section 3 on estimation and reporting of mineral resources. In this section, there are concise guidelines outlining the fundamental requirements for estimation bulk density. The competent persons have the responsibility to ensure that the bulk density estimates are reliable and robust. This entails employing a sound sampling methodology that is appropriate for the specific deposit. They must oversee the entire process and implement various QA/QC procedures, and additionally, they are expected to provide a discussion on how the bulk densities were estimated based on the results of sample density analysis. When it comes to 3D modeling, density can be just statistically modeled in a similar manner as the metal grades of the mineral deposit. This approach allows for creation of unbiased 3D models of the variables under study. Furthermore, it enables the estimation of model uncertainties and or estimation errors, which play a crucial role in the non-subjective classification of the mineral resources. So let's look at the example provided in the book Applied Mining Geology by Abzalov. Using geostatistical models, the uncertainties or estimation errors of the ore reserves were estimated for both rock densities and metal grades. These estimation errors were then plotted against the corresponding sampling distances. The plotted diagrams clearly illustrate that the estimation errors for rock densities consistently remain lower than those for metal content. This suggests that the accurate estimation for rock densities for purpose of classifying ore reserves that can be achieved using significantly fewer samples compared to the number needed for modeling metal grades at the same deposits. So to summarize, it can be inferred that geostatistically optimized grids for measuring rock densities are usually positioned between the chemical assay grids needed for estimating proved and probable reserves. Now, let's dive into the interesting aspect of assessing mineral resources in polymetallic deposits. When dealing with these types of deposits, it can be quite helpful to present the results in terms of the metal that contributes the most value. In essence, the primary mineral chosen for reporting on metal equivalent basis is the one that holds the highest value in the deposit. The secondary minerals, on the other hand, are multiplied by their respective current minerals prices and then divided by the current mineral price of the primary mineral. This calculation allows us to determine the mineral equivalent value. So, why do we bother with all these calculations? Well, Calculating the metal equivalent grade of polymetallic deposits serves to simplify the evaluation process. By expressing the ore body in terms of an equivalent grade of one mineral, we can make comparisons and assessments much more straightforward. The calculation of the equivalent grade relies on two important factors: metal price of each commodity and the process recovery of each commodity. To put this in practice, we can take a look at the deposit of complex ores such as tin, tungsten, or iron. Let's consider how we can recalculate the equivalent grade in K-mine. So the equivalent grade represents the combined values of co-products, tin, tungsten, and magnetic recovery percentage of magnetic iron normalized in the value of tin. The calculation for equivalent grade can be done by using formula that you see on the slide. By using this equation, we can determine the equivalent grade percentage that takes into account the contributions of tin, tungsten, and magnetic recovery percentage of magnetic iron. It's a valuable approach to assess the overall value of the deposit based on these different minerals. To streamline the process, we use database triggers to automatically recalculate the main component based on the equivalent grade percentage formula. This ensures efficient and accurate updates within the system. The tin equivalent formula takes into account different pricing factors for each component. I considered a tin metal price of $22,000 per ton, and APT or ammonium para tungstate price of $375 per MTU, which is 10 kilograms of tungsten, and magnetite concentrate price of $105 per ton. These values help calculate the tin equivalent grade, providing a way to compare the combined values of tin, tungsten, and magnetic recovery percentage of magnetic iron in terms of their contribution to the overall value. So the result of calculation saved in the column tin equivalent. With a trigger, we can assign drill hole intervals that meet certain criteria, like cutoff grade. That means that if equivalent grade percentage is greater than or equal of 0.4%, then we enter code 1 in the grade column. If not, then code 2. So today we're not gonna dive too deep into the specifics of ore body delineation, wireframe creation, or block modeling, or just statistical analysis. If you're interested, we have previous webinars on our channel where you can watch the step-by-step process of performing these operations in K-mine. So feel free to check them out for more in-depth understanding. I'd like to highlight, though, that K-mine offers a user-friendly and versatile toolkit for visualizing drill hole data and block models. With our software, you can easily explore and analyze your data intuitively. And by using graded field, we can visually represent the variation in grades within blocks and identify regions with higher grade ore bodies. The block scoring was done by using the ordinary Kriging method. Now let's visualize the resource categories and calculate volumes, tonnage, and average content of the ore. All right, so now you can see the variation in grades within the blocks, and you can identify regions with higher grade ore bodies. So now we visualize in the resource categories and calculating volumes, tonnage, and average content of the ore. In the result window, you will find a built-in formula tool for performing recalculations. So for instance, let's add a column and calculate the amount of tin in tons within the ore. In the formula field, we input equal tonnage multiplied by grade percentage divided by 100,000 tons. We can also include a total row to calculate the sum or average values. The table can be exported in CSV and XLS format. So if needed, we can conduct a grade tonnage curve analysis. We specify the cutoff grade steps, such as 0.1%, and the calculation results also can be exported in a CSV or XLS file, allowing us to analyze the tonnage and average grade in the ore at each cutoff grade value. So let's once again refer to the JOR code and take a closer look at the requirements it sets for the report. In clause 50, we will find that when reporting exploration results, mineral resources, or ore reserves for polymetallic deposits in terms of metal equivalents, certain details needed to be included to adhere to the principles of transparency, materiality, and competence. We see 5 bullet points. Individual grades for all metals involved in the metal equivalent calculation must be provided. Assumed commodity prices for all metals should also be disclosed. Simply referring to a spot price without disclosing the actual price used in the metal equivalent calculation is just not sufficient. However, if the actual prices are used commercially sensitive, the company must provide enough information, possibly in a narrative form, for investors to just understand the methodology behind determining these prices. Number 3, assumed metallurgical recoveries for all metals need to be stated, along with a discussion of how these recoveries were derived, such as through metallurgical test work, detailed mineralogy, or similar deposit. A clear statement must be also included expressing the company's opinion that all elements included in the metal equivalence calculation have a reasonable potential to be recovered and sold. And finally, the calculation formula for metal equivalents should be specified. So typically when reporting metal equivalence, it's advisable to choose the metal that contributes the most to the calculation. However, if another metal is selected instead, the report must provide a clear explanation why. To have meaningful metal equivalence is crucial to estimate the metallurgical recoveries for each metal. If there is no reliable estimation of metallurgical recovery information available, then just reporting metal equivalence would not be suitable. Also worth to mention that when it comes to exploring new projects, getting accurate metallurgical recovery information can be quite tricky. In fact, it's often not just feasible to obtain or confidently estimate those recovery details. So if we rely on reporting metal equivalents in these situations, we just might end up with misleading conclusions and interpretations. All right, so let's see if we have some questions here. I would like to include in this conversation our geologist Tatiana. Yes, hi. Hi again. So one of the question is, how can resource categories be delineated in the early stages of exploration when there are still large distances between drill holes? And like how to avoid the spotted dog effect, and is everything categorized as inferred?
At the early stage of exploration, the generated data are insufficient for estimation of mineral resources and ore reserves. However, it might be of use to investors, therefore it's reported as exploration results. These usually include results of outcrop sampling, geochemical exploration data, and geophysical survey results. In general, if a company reports the exploration results, then estimates of tonnages and average grade usually are not assigned to the mineralization. Alternatively, if the company has chosen to discuss and report the exploration results in terms of the size of the exploration target, it should be quoted as a range of tons and range of grade.
Great, thank you. Another question is, can mineral resources and reserves be evaluated outside the final pit contour? So what should I do if some of the inferred category resources fall into the pit contour?
It's a very popular question. Thank you. Resources falling outside of the pit shells are not be converted to the reserves because they are not economically mineable and the economic and technical parameters used for construction the pit models. However, these are still can be reported as mineral resource in case if they pass the requirement for reasonable prospects for eventual economic extraction. The same is related to inferred resources, which cannot be converted to ore reserves because of a low confidence in their tonnage and grade. There are usually some inferred resources within mine plan, and sometimes it makes sense to include inferred resources in a mine plan and schedule. The JERC code does not stop us using inferred resources in a mine plan, but it does guide us how they should be used for estimating and reporting ore reserves. It also should be noted that if there are no reasonable prospects for eventual economic extraction, then regardless of the geological and sampling data available, a concentration of solid material of economic interest cannot be defined as a mineral resource in accordance with the JERC code. Possible examples, scenarios where a concentration of solid material of economic interest will not have reasonable prospects eventual economic extraction could include, for instance, a deposit at a depth too great to be economically mined for the deposit grade, a deposit within a national park or heritage site, and deposit in a country that has a political restriction or war. So you should be attentive in your resource estimation with this inferred category.
And the other question is, what is more important than when evaluating metal equivalent, price or recovery?
Both. Calculation of metal equivalent dependent on assay data, metal mineral pricing, and metallurgical recoveries. Clause 50 from the drug code tells us about the requirements for reporting of metal equivalent. Among them, reporting individual grades for all the metals, assumed commodity prices for all the metals, assumed metallurgical recoveries for all metals, and how derived, a clear statement that all elements have a reasonable potential to be solved. It's very important. And show the calculation formula, of course. So the companies like to expand their results sometimes, and they use every element possible to include in their equivalent calculations. Sometimes unrealistic metal ratios, high prices for the byproduct metals and low prices for the metals that they are calculating equivalent values for. And the most popular lapses, they will provide recovery percentage for some, but not all of the metals used to calculate the equivalent grades. For the metals without a recovery value, the company used 100%. So reporting on the basis of metal equivalent is not appropriate if metallurgical recovery information is not available or able to be estimated with reasonable confidence. And for many projects at the exploration result stage, metallurgical recovery information may not be available or able to be estimated with reasonable confidence. So in such cases, reporting of metal equivalent may be misleading, of course.
We have another comment here. Somebody said, AQR method sometimes cut too much data. What do you think about that?
Yes, it depends on the type of mineralization, of course, and the size of your deposit and your distribution for samples. So it depends on too much factors, of course.
Yeah. Well, thank you so much. I think that is all the questions. Again, it's Tatiana, our geologist. Thank you so much for your time. I want also to mention that if you're interested to try K-Mine, currently we are offering free proof of concept. So basically, if you want to see how your workflow can be done in K-Mine, how we can optimize, streamline your process within our one interface that compose all of these models, feel free to reach out. We will be happy to chat and discuss and tell you more about how it can be done. I think that is it for today. Thank you so much, everyone, for joining, and I'll see you next time on our next stream. Thank you.
Thank you, Anna. Bye.
Thank you. Bye.